Okay, so we will discuss a few more problems. The first problem is 1 mole of an mole of a monoatomic ideal gas for which gamma is Cp by Cv. So, gamma is 5/3 at 27 degrees Celsius is adiabatically compressed in a reversible process from an initial pressure of 1 atmosphere to a final pressure of 50 atmosphere. Calculate the resulting difference of temperature. So, the first problem states 1 mole of a monoatomic ideal gas for which gamma is 5/3 at 27 degrees Celsius is adiabatically compressed in a reversible process from an initial pressure of 1 atmosphere to a final pressure of 50 atmosphere, and we need to calculate the resulting difference of temperature. So, we need to first calculate the final temperature for this adiabatic process. So, we have P1 is the initial pressure and the value of initial pressure is 1 atmosphere. P2 is the final pressure and the value of P2 is 50 atmosphere. Initial temperature is given. So, T1 is the initial temperature which is 27 degree Celsius, means 300 Kelvin. So, the initial temperature is 300 Kelvin and we need to calculate T2 is what? This is the final temperature. We know for adiabatic process P2 by P1 to the gamma minus 1 is T2 by T1 to the gamma. Now, gamma is 5/3. So, we get 50 to the 5/3 minus 1 is T2 by 300 to the 5 by 3. So, it gives us 50 to the 2 by 3 is T2 by 300 to the 5 by 3. If we take log, so we get 2 by 3 ln 50, we get 5 by 3 ln T2 minus 5 by 3 ln 300. So, if we solve it, we get T2 is 1434.5 Kelvin. So, we have calculated the value of final temperature. So, the resulting difference in temperature, the resulting temperature difference is nothing but T2 minus T1. So, we get 1434.5 minus 300 Kelvin. So, we get 1134.5 Kelvin, nothing but 861.5 degree Celsius. Okay, so, the resulting temperature difference is 861.5 degree Celsius. Okay, so, next problem now we discuss problem number 2. An ideal gas expands reversibly according to the equation PV to the n equals to A, where A is a constant, where A is a constant. So that the heat absorbed by the gas is W times gamma minus n by gamma minus 1, where W is the work done by the gas during the process. So, the second problem is an ideal gas expands reversibly according to the equation PV to the n equals to A, where A is a constant term, so that the heat absorbed by the gas is W times gamma minus n by gamma minus 1, where W is the work done by the gas during the process. Okay. So, it's a very important problem. So, how we will solve it? Okay. So, for a reversible transformation, we can write del Q reversible is Cv times dt plus Pdv. This one we get from first law of thermodynamics. Okay. So, we get Q is Cv, or Q reversible is Cv is V1 to V2, P is okay. So, here T1 is the final temperature and T2 is the T1 is the initial temperature and T2 is the final temperature, and V1 is the initial volume and V2 is the final volume. We are considering Cv is a constant term here. So, what we consider here, considering Cv is constant or independent of temperature, T1 is the initial temperature T2 is the final temperature Similarly, V1 is the initial volume and V2 is the final volume. So, we get from above, we get Q reversible is Cv T2 minus T1 plus A times V2 to the minus n plus 1 minus V1 to the minus n plus 1 by minus n plus 1. So, this is the value of Q reversible. Okay. So, if you further simplify, we get Q reversible is Cv times T2 minus T1 plus P2 V2 minus P1 V1 by 1 minus n. So, we get Q reversible is Cv times P2 V2 minus P1 V1 by R, we consider 1 mole here, plus P2 V2 minus P1 V1 by 1 minus n. So, we get Q reversible is P2 V2 minus P1 V1 by 1 minus n times Cv 1 minus n by R plus 1. So, here we consider 1 mole of an ideal gas. Okay. So, we get Q is P2 V2 minus P1 V1 by 1 minus n times Cv times 1 minus n by r plus 1. But the work done W work done by the gas W given by the above equation 1. So, equation number 1 is the first equation we consider. Okay. So, by the equation 1 is W is P2 V2 minus P1 V1 by 1 minus n. So, we can write Q reversible is W by times 1 minus n by gamma minus 1 plus 1, or we can write Q reversible is W times gamma minus n by gamma minus 1. Okay. So, we can prove that Q is gamma W times gamma minus n by gamma minus 1. So, it is proved. Next, we consider another beautiful problem, a reversible problem number 3. A reversible engine converts one-sixth of the heat input into work if the temperature of the sink is reduced by 62 degrees Celsius, its efficiency is doubled. Find the temperature of the source and the sink. So, efficiency of the engine is so you need to look at Carnot cycle, which was not discussed, but it was assumed that you know what is Carnot cycle, but the students who do not know what is Carnot cycle, so it is advised that okay, you read it. It is very easy to understand. So, the efficiency of the engine eta is 1 by 6 is 1 minus T2 by T1, where T1 is the temperature of the source and T2 is the temperature of the sink. So, T2 by T1 is nothing but 1 minus gamma So 5 by 6. Suppose this is our equation number 1. Now, if theta prime is the efficiency of the engine when the temperature of the sink is reduced by 62 degree Celsius. So, we can write eta prime is 2 times 1 by 6 is 1 minus T2 minus 62 divided by T1. So, we can write T2 minus 62 by T1 is 1 minus 1 by 3, or we get 2 by 3. So, this is our equation 2. So, if we divide equation 1 by equation 2, we get, so your equation, if we divide equation 2 1, so dividing equation 2 by equation 1, so we get T2 by T2 minus 62 equals to 5 by 6 times 3 by 2. So, we get 5 by 4. So, we get 5 T2 minus 310 equals to 4 T2. So, we get T2 is 310. So, this is the temperature of the sink. Okay. So, temperature of the source is, so we again we have T2 by T1 equals to 5 by 6. So, T1 is 6 T2 by 5. So, 6 times 301 by 310 by 5. So, we get 372. So, the temperature of the source is 372 Kelvin, and the temperature of the sink is 310 Kelvin. Okay. So, we will discuss one more problem. Problem number 4 is 10 gram of water at 60 degrees Celsius is mixed with 30 gram of water at 20 degrees Celsius, will the entropy of the resulting system increase or decrease. Calculate the change in entropy. Calculate the change in entropy. So, the fourth problem is 10 gram of water at 60 degrees Celsius is mixed with 30 gram of water at 20 degrees Celsius. Will the entropy of the resulting system increase or decrease? Calculate the change in entropy. So, we are mixing 10 gram of water at 60 degrees Celsius with 30 gram of water at 20 degrees Celsius. So, we need to calculate the final temperature first. So, suppose the final temperature after mixing of 10 gram of water at 60 degrees Celsius and 30 gram of water at 20 degrees Celsius. Suppose the final temperature is T degrees Celsius. So, if we mix 10 gram of water at 60 degree Celsius with 30 gram of water at 20 degrees Celsius, so the temperature of the 10 gram of water at 60 degrees Celsius will decrease. Okay. Similarly, the temperature of 30 gram of water at 20 degrees Celsius will increase. Okay. Now, if and here you consider the final temperature is T degrees Celsius. So, you can write 10 times 1 times 60 minus T equals to 30 times 1 times T minus 20. Okay, so we get 600 minus 10T equals to 30T minus 600. So, we get 40T equals to 1200. So, we get T is this gives you that. So, the resulting temperature resulting or final temperature is 30 degrees Celsius. Now, the change in entropy, now the change in entropy of 10 gram of water due to change in temperature from 60 degrees Celsius to 30 degrees Celsius is Now, the change in entropy of 10 gram of water due to change in temperature from 60 degrees Celsius to 30 degrees Celsius is delta C1 is m c ln T2 by T1, where T2 is, or first T1 we consider, T1 is 660 plus 273 Kelvin, so gives 333 Kelvin, and T2 is 30 plus 273 Kelvin, so 303 Kelvin. So we get delta C, delta S1 we say, delta S1 is 10 times 1 times ln 333 by 303. So if we calculate this one, we get delta S1 is minus 0.944 calorie per Kelvin. Now the change in entropy of 30 gram of water due to change in temperature from 20 degrees Celsius to 30 degrees Celsius is delta S2 is M2 times C times ln T2 by T1. M2 is the mass of water, so M2 is 30 times 1 times ln initial temperature, final temperature is 303 and initial temperature is 293. So we get delta S2 is 1.007 calorie per Kelvin. So total change in entropy, total entropy change due to mixing, so delta S mix is delta S1 plus delta S2, and we get 0.063 calorie per Kelvin. Since delta S mix is positive, thus the entropy of the resulting system will increase. Okay, so this is from entropy of mixing this problem was based on. Okay, next problem is problem number 5. Two bodies of equal and constant thermal capacity means heat capacity, wall capacity C at absolute temperatures T1 and T2, where T1 is greater than T2, respectively, attain the same temperature on being placed in direct thermal contact. Calculate the loss of available energy. So, problem number 5 says two bodies of equal and constant thermal heat capacity C at absolute temperatures T1 and T2 respectively attain the same temperature on being placed in direct thermal contact. Calculate the loss of available energy. Okay. Now, here you have one thermal body of temperature T1 and you have another thermal body of temperature T2 and they are brought in thermal contact with each other. So, this is what is happening there. Okay. Now, we consider if Tc be the common final temperature of the two bodies, then we can write C times T1 minus Tc is to C times Tc minus T2 as T1 is greater than T2. So, this is first body, suppose this is second body. So, since the temperature of the first body is higher than the temperature of the second body, so the first body will lose heat and the second body will gain heat. So, we get Tc is half times T1 plus T2. So, here we are considering, we also consider here considering both the bodies have equal masses, okay, then only it is valid. Okay. So, this is the final temperature. So, the entropy change of the first body, the entropy change of the first body, if we say that is delta S1 is m times C ln Tc by T1, and the entropy change of the second body we say the entropy change of the second body is delta S2 is nothing but mc ln Tc by T2. Okay, so total entropy change we say delta S is delta S1 plus delta S2. So, we get delta S1, delta S is mc ln Tc by T1 plus mc ln Tc by T2. So, we get delta S is m C ln Tc plus or minus mc ln T1 plus mc ln Tc minus mc ln T2. So, we get delta S is twice mc ln Tc minus mc ln T1 times T2, or we get delta S is mc ln Tc to the 2 minus mc ln T1 times T2. So, you get delta S is mc ln Tc to the 2 times T1 times T2. So, this is the total entropy change for this process. So, we get delta S, total entropy change of this process is m times C times ln Tc to the 2 by T1 times T2. Now, we substitute the value of Tc here. If we do it, we get delta S is m C ln T1 plus T2 to the 2. So, you get delta S is mc ln T1 plus T2 to the 2 by 4 times T1 times T2. If now, if T0 be the lowest available temperature, the amount of available energy is T naught times del S. So, you get T naught times mc ln T1 plus T2 to the 2 by 4 times T1 times T2. So, this is the answer. Now, problem 6. the molar specific heat capacity at constant volume of diamond varies with temperature. As CV is 3R times 4 pi to the 4 by 5 times T by theta d to the 3. Where theta d is the Debye temperature calculate the change in entropy in units of R, gas constant R, of 1.2 gram of diamond when it is heated at constant volume from 10 Kelvin to 350 Kelvin, given atomic weight of diamond, atomic weight of carbon is 12 and theta d is 2230. So, theta d is 2230 Kelvin. Okay, this is another very good problem. Thus, it says the molar specific heat capacity at constant volume of diamond varies with temperature as Cv equals to 3R times 4 pi to the 4 by 5 times T by theta d to the 3, where theta d is the Debye temperature. Calculate the change in entropy in units of R of 1.2 gram of diamond when it is heated at constant volume from 10 Kelvin to 350 Kelvin, given atomic weight of carbon is 12 and theta d is 2230 Kelvin. So, change in entropy is given by delta S is n Cv dt by T. So, n is, so here n is 1.2 by 12, 0.1. So, we get delta S is 0.1 times temperature changes from 10 Kelvin to 350 Kelvin, and value of Cv is 3 or rather 12 by to the 4 by 5 times R times T to the 3 by theta d to the 3 times So, we get delta S is 0.1 times 3r times 4 pi to the 4 by 5 theta d to the 3 0 to 10 to 350 t to the 2 dt. So, we get delta S is 0.1 times 3 times 4 times 3.14 to the 4, that is the value of pi, times r by 5 times 2230 to the 3 times 1 by 3 350 to the 3 minus 10 to the 3. So, if you integrate t to the 2 dt, we get 1 by 3 t to the 3, and if we substitute the value of initial and final temperature, we get 1 by 3 times 350 to the 3 minus 10 to the 3. So, we get delta S is 0.30 r. This is simple but very good problem. Problem number 7. Calculate the efficiency of the cycle A, B, C, D, A as depicted in the temperature entropy diagram, TS diagram, given in the figure below. In terms of T1 and T2, given AC equals to BD. So, this is the figure. Now, we read the problem once more. Calculate the efficiency of the cycle ABCDA as depicted in the TS diagram given in the figure below in terms of T1 and T2, given AC equals to BD. The solution. In the TS diagram, the heat absorbed is given by Q equals to area of ABC equals to area of semicircle ABCA plus area of rectangle AC S1 S2. So, you can write Q is half times pi BD by 2 to the 2 plus AS2 times AC. So, we get Q is half times pi T1 minus T2 to the 2 plus T1 minus T2 by 2 plus T2 times T1 minus T2. So, we get Q is 1 by 8 times pi T1 minus T2 to the 2 plus half T1 plus T2 times T1 minus T2. So, this is 8. Okay. So, this is the heat. So, work done W is given by W equals to area of the circle or area of the cycle ABCD. You get W is pi times BD by 2 to the 2. So, you get pi by 4 T1 minus T2 to the 2. So, the efficiency of the cycle so the efficiency of the cycle A B C D A is given by eta is work output by heat input. So, we get eta is pi by 4 times T1 minus T2 to the 2 by pi by 8 times T1 minus T2 to the 2 plus half T1 plus T2 times T1 minus T2. So, you get eta is twice T1 minus T2 by T1 minus T2 plus 4 T1 plus T2. So, we get eta is 2 times T1 minus T2 by 5 T1 plus 3 T2. So, this is the efficiency, which is equal to 2 times T1 minus T2 by 5 T1 plus 3 T2. Now, problem 8. Determine the values of CV, CP and gamma is CP by CV for SO3 gas. So, this is a problem which requires little conceptual ability. The problem says determine the values of CV, CP and gamma for SO3 gas. So, solution: SO3 molecule is non-linear, So, the internal energy per mole U is U translational plus E rotational. So, we get U is 3 times 1 by half RT plus rotational is 3 times half RT. So, we get 3 RT, U is 3 RT. So, CV is del U by del T at constant volume. So, we get 3R. So, CP is CV plus R. So, we get 3R plus R, 4R. So, gamma is CP by CV. So, we get 4R by 3R, we get 4 by 3. So, that is the value of gamma. Problem number 9. For the reaction twice NO gas plus O2 gas equals to 2NO2 gas, the value of delta H is 113.1 kilojoule. If 6 moles of NO reacts with 3 moles of O2 at 1 atmospheric pressure and 298 Kelvin temperature to form NO2, calculate the work done in kilojoule unit against a pressure of 1 atmosphere. What is the internal energy change delta U for the reaction? Okay. So, problem number 9 says for the reaction 2NO gas plus O2 gas equals to 2NO2 gas, the value of delta is 113.1 kilojoule in kilojoule unit. If 6 moles of NO reacts with 3 moles of O2 at 1 atmosphere and 298 Kelvin temperature to form NO2 gas, calculate the work done in kilojoule unit against a pressure of 1 atmosphere. What is the internal energy change delta U for the reaction? Okay. At constant pressure, the solution is at constant pressure W is minus P times del dV, right? So, V2 minus V1 del V. So, minus into T minus N1 on T. So, temperature is constant here. So, we get W is minus N2 minus N1 times T. So, we get minus N2 is the product number of moles of the products. Okay, so that is our 6, right? 6 minus 6 plus 3 times RT. So W is minus plus, so 3 times RT. So 3 times 8.314 times 298. Okay. So gives us 7.432 kilojoule. Now delta N for the reaction is 2 minus 2 plus 1 is 2 minus 1. So delta U is delta H minus delta N RT. So we get delta U is minus 113.1 times minus 1 times minus 1 times 8.314 times 298 by 1000. So you get delta U is minus 110.62 kilojoule. Thank you.